Hi, in this video, we want to take a look at ways to find transformations for our target variable. All right, so here we've got a linear regression model, and we would like to, after looking at the scatter plots, looking at the diagnostics, we would like to improve our model by transforming our variables. Well, what we're going to do here, we're only going to transform the target variable. Now, we're in multiple linear regression, so I could transform each of the predictor variables, or I could try and find like other predictor variables to include, such as interaction terms. But for now, we're just going to focus on transforming one variable. So in this example, we're going to go through and we're going to look at two different ways that we can find suitable transformations. And we're going to be talking about exponential transforms this time. Well, it's going to, as we work through this, we're going to see that we're going to get exponents that are close to 0.5. And since they're close to 0.5, and our diagnostics show that 0.5 would be reasonable, and we're only getting estimates off of these tools, that we'll go ahead and go with the square root transform instead of the ones that are put out to us by the algorithms. Now, why do we do that? So remember that my goal when I'm doing analytics frequently is not to get the best model possible, it's to get the most useful model possible. So something that I always need to do, I always need to think about, what is it that my audience will accept? Well, will they accept a 0.44 exponent? Like what does a 0.44 exponent look like? I know, but I have a PhD in math, so I'm not the target audience. Most people are not going to be comfortable with exotic exponents for their transformations. But 0.5, I can say square root. A lot more people will be comfortable with a square root than a 0.44 exponent. So in most situations, I prefer to go either with integer values or 0.5 for exponential transforms if I'm going to be doing it. All right, so let's go ahead and start working on it. So I'm going to load the data, and this is the defects data set from the textbook. And one thing I'm going to do, which this is very typical of my videos, is I sort the data by the target variable, and then I rename the rows to go with the order of the sorted order of the target variable. Why do I do that? When I look at my diagnostic plots, I have the order corresponds to the rank of the target variable, makes it easier for me to spot features in the data. Now let's go ahead and color the points. Now for this video, it's coloring the points. It's not going to be a big deal, but I always do this personally and I do this at work every single time because it helps me find features in the data that I wouldn't have spotted otherwise. In fact, I was working with one of the students in the class, and I was able to spot things in his data because he colored it that he missed. And so that's a good example of times that it paid off. All right, so now let's go ahead and look at the pairs plot. Let's look at, so what I'm going to do, I'm going to take defective, depends on temperature, density, and rate. Now, I don't know what this data says all about, but here are the predictor variables. Here is the target variable from the example in the textbook, and I'm just running with it. And I'm using plot character 21. This puts a black circle around it, and then the center is colored. And when we look at this, so here we've got defective on our y-axis. Here we have temperature on the x, density on the x, and rate on the x. And you can see that it's like there's a curvature. There's a curvature and there's a curvature. Okay, so a linear regression model with degree 1 terms probably is not going to be the best fit I could possibly get. Now I notice that temperature and density look like there's a correlation between them. Temperature and rate also. Density and rate also. So I'll also want to be mindful of the possibility of overfitting on this model. Okay, so let's go ahead and build the vanilla model. And I'm going to change this to vanilla instead of initial. All right, so here I've got the vanilla model in all degree 1 terms. predicting defective. And let's go ahead and take a look at what we've got. All right, so here I see that temperature looks like it's pretty close to statistically significant, but you know, the other two are not. And this one isn't even under 0.05. I mean, that's kind of surprising. Now, but when I look at the R squared, it's not, for real life data, that's actually not too bad. A 0.87 or 0.88 and 0.87, that's pretty good. The Anova test says that there is something informative in my predictor variables. There's something going on. I might have a collinearity issue that's jumping out at me because of the scatter plot. Okay, so now let's go ahead and run Anova. Remember, Anova is going to go through, and on this line, it's a hypothesis test, is that should we add temperature to the constant model? Yes, we should. Then after that, should we add density to the simple linear regression model with temperature? Here, that one, that's, you know, that's a maybe, maybe not. That's up to our subject matter knowledge and our professional opinion. Now, should we add rate to the model with density and temperature? Here, probably not, but we're going to go ahead and proceed anyway because that's what's in the example from the book. So here, honestly, I am having concerns about collinearity between the three of these. That if I was doing this in real life, I would start exploring the model with just temperature and density. But well, that's for another day. All right, so now I'm going to take the standardized residuals and slap them onto the data frame. I'm going to take the fitted values and slap them onto the data frame. That way I can plot them in a moment. So let's go ahead and plot the standardized residuals by temperature. Remember, the standardized residuals are centered on 0 and rescaled to have standard deviation 1. And I don't want to see a pattern. So now something that is, so I see that temperature is going along here. If temperature is correlated with the target variable, then I would expect the color shift to go along temperature. To my eyes, I see the color gradient going along this way, which is something that might be an issue. We'll keep digging into this. All right, now let's check out density. So for density, to my eyes, it looks like there's kind of like a color gradient going this way. I would rather it go horizontal. But otherwise, on the dots, I don't really see an issue. Now, this really isn't very many dots for, or very many data points for a linear regression model. If you think you see a trend, I'll grab like one dot, like the most extreme dot, and move it around in your mind. And if that pattern that you see with your eyes disappears, then there probably isn't a pattern. 1 point, if you can move 1 point and change your visual interpretation of a scatter plot, you don't have a pattern. Now let's check rate with the standardized residuals. And yeah, I'm kind of seeing this one, I'm not seeing as much of a color gradient. It's more the way I want it to be. All right, now let's look at the standardized residuals versus the fitted values. And this is going more along the lines of what we want to see in terms of color. And I'm not really seeing a pattern. All right, so that's all right, that's good. But, you know, remember, none of it was really statistically significant, right? You know, I was like, man, temperature wasn't really statistically significant, but it's okay for the Anova test. I'm real confused. I don't know what to do. Okay, let's keep on going. Let's look at defective versus fitted values. So here, this is the actual observed value, and here is the modeled value. And we're going to plot this. if I have a good model, the line should be a good representation. So what I'm doing here is, if I have a good model, the fitted values and the defective values should go along the line y equals x. And this is here. So here the y-intercept is 0, slope is 1. All right, so if I've got a solid model, the points from here will be tracking pretty well for this straight line. So let's take a look. And I mean, this isn't too bad. Have some points over here, and then like a lot of points over here below it. So I mean, it's not too bad. You know, it might be happenstance I don't have points up here. Don't know, not 100% sure. But I mean, there might be some curvature here. I don't know, I'm not real sure. You know, if I move one point, if I take this point and move it down, that impression that I'm getting would disappear. So I'm not real confident either way, but I'm not feeling good about the output I had initially. Remember that none of my coefficients were really that strong in terms of the hypothesis test. All right, so let's go ahead and go, you know what? Let's go ahead and just try a transformation on the target variable. Let's see if we can make something better. All right, so we've got two plots to do this. We have an inverse response plot, and then we have a box Cox plot. Let's do the inverse response plot first, and it's in the car package. So I just drop in the model. Now, something you have to do, you have to tell the transformation values that you want to explore. And so we'll go from -1 to 1, and I'm just going to move by 1/2. Now, before this video, I played around with a lot of different values. The plot that's generated like overlapped the lines a lot. So I ended up going at a step of 0.5 when I was exploring. I tried 0.1, I tried 0.25, but to visually get what I wanted off the plot for teaching purposes, 0.5 looked pretty good. Okay, so this plot is saying 0.44 is its estimated value for the best transformation possible. Okay, well, let's look at this. Do you see this gold line? This gold line is 0.5. I mean, that's pretty, the gold line and the black are really close. UCF colors, right? That's my happenstance. So they're pretty close. Now think about 0.44 and 0.5. 0.5 is the square root. 0.44 is something that we really haven't dealt with. Like, you know, I can talk to college algebra students and they'll nod their heads at it and they'll go with it. But, you know, really people in day-to-day life, I mean, they don't even deal with square roots very often. Exponent of 0.44, I'm kind of feeling like, you know, 0.5 would be a better choice. Now here's the lambda value, and here's the residual sum of squares. And we can see that 0.5 has a substantially better value than the others, and 0.44 isn't too far off from 0.5. All right, well, let's do this again, but this time I'm going to help like zoom in, I'm going to reduce the value, the different values for the lambda. This way I can see that visualization a little bit better to give myself a better impression of what's going on. All right, so all we've got are 0.25, 0.5, 0.75, and all of them are actually pretty close. Honestly, I think all three of these would be reasonable choices. Now, the algorithm is saying 0.44 is the best. Now, remember, you know, I always have to be mindful of the goal of the project. If my goal is to get the best prediction possible, I want 0.44. But if I need to get people to believe in my model, to have faith in it, I need to make sure that they are mathematically comfortable with it. And at 0.5, they're going to be more comfortable with. So right now, I'm leaning towards a square root transform. And here it just repeats the output from previous. Now let's do the Cox Transform. And here we're going to be doing plots. So we're going to have a whole bunch of lambda values. Now here you'll notice I have a lot more lambda values for this than where I had previously on the inverse response plot. All right, so here I can see that there is a log likelihood confidence interval going on. So what this is trying to do, this is trying to find the maximum log likelihood. So remember, maximum likelihood estimates. So this is, conceptually very similar to that. That is trying to find the maximum likelihood estimates, and then it's giving me like a confidence interval. All right, well, here, these values aren't very zoomed in. It's hard for me to tell. I know it's around 0.5, but I want something a little bit more precise. So now let's go ahead and zoom in. So what I'm going to do, I'm going to do the same thing, but now I'm going to limit lambda to values that are zoomed in. And I did this by exploring different visualizations before I made the video. What I did, I looked here and I went from 0 to 1, and then I looked at the visualization and I took like the next two values and the next two values. I zoomed in until I got 0.3 to 0.6. And if I wanted to, I could keep on zooming in to get a more refined picture, but there's really no point. So I'm good with what I've got right here. All right, so I can see I've got a 95% confidence interval. All right, that's pretty good. So I'll notice that 0.5 is in there. 0.5. So any value inside here. So this visualization indicates that any value along this range between the vertical dashed lines, the far left and the far right, would be reasonable. It's saying that about 0.45 is the best way to go by the estimate. But remember, that's just an estimate, right? Since it's an estimate, it's going to be a little bit off. And 0.5 isn't too far off. It's within that interval. And I know that operationally, 0.5 is going to be a more accepted value. So I'm leaning towards 0.5. All right, so what I'm going to do, I'm going to explore the square root transform model. So I'm going to take square root of defective, and I'm going to model it with the predictor variables like I had previously. All right, now look here. Does that look like it's straighter? Yes, it does. Does that look straighter than it did before? Yes, it does. Does that look straighter? Well, I've got these points right there kind of sticking down, kind of peculiar. But we really weren't feeling it for rate anyway. So, overall, I'm feeling like this is a better model. Okay, so let's go ahead and do a scatter plot of the square root of defective by temperature. So here I'm zooming in on that top row of pairs plots. And I'm feeling better about this being a straight line. Let's keep on going. All right. Density and the square root of the target variable. Now we've got rate and defective. So here, these points are kind of sticking out, kind of strange looking to me. And honestly, if I moved one point, I would still kind of see a straight line there. So I'm kind of wondering what's going on. I would want to dig into that further. Okay, so now let's actually build the model with the square root transform, because now I'm convinced that it's a better way to go. All right, and when I do this, remember that temperature really wasn't even statistically significant. Density wasn't, and rate was even worse. Now, I can see that temperature is statistically significant, density is statistically significant, and rate is still above 0.05, but it looks a lot better. I'm still leaning towards excluding rate if this was a real project. remember what I had for r squared? It was 0.8 something each time. Now I'm better than 0.9. That's, I mean, in the greater my r squared is, the harder it is to improve. So going from 0.8 something to 0.9 something, that's a big improvement. Now let's go ahead and look at the Anova table. Should we add temperature to the constant model? Yes, we should. That is within machine accuracy. Now, should we add density to the simple linear regression model with temperature? Yes, we should. Should we add rate? Maybe, maybe not. That'd be up to subject matter experts. But just going off of what I've seen so far, I'm leaning towards excluding rate from the model. All right, now let's go ahead and evaluate the transform model. So I'm going to tack on the standardized residuals and the fitted values onto my data frame. That way I can plot them easily. All right, so let's look at the standardized residuals. And I don't see a pattern. The color gradient appears to be gone. That's making me feel better. So everything looks like the colors are shifting horizontally and not obliquely. Let's do the standardized residuals versus density. And this is an improvement. There might be something still going on with the color, but I'm not going to sweat this. And then rates. There might be a color gradient a little bit shifted, but we didn't like rate anyway, so whatever. All right, now let's look at the standardized residuals versus the fitted values. And this is much improved. Not much improved, it's just improved. Remember, when I look at these scatter plots with residuals, I don't want to see a pattern in the dots. If I see a pattern in the dots, there's a problem. All right, so now let's go ahead and plot the square root of defective by the fitted values. Now this looks much better. I don't see anything that could be interpreted as curvature away from the line. I'm feeling good. I think that this was a good model to go with. Now that we feel comfortable with this model, let's go ahead and do some other model diagnostics, like the standard diagnostic plots. All right. So here, remember that this line is going to find a pattern. This line will always find a pattern. If it looks like it's just a scribble, usually you don't have to worry about it. But if I see like a smiley face or a frowny face, something like that, there's a problem. Ooh, these points are kind of poking out. Might want to investigate those further. 15 and 23 and 3. Now, something that's nice about this, because I relabeled the values, I know that these are not extreme values for my y's. So remember that whenever I have extreme values of x, then I'm going to have more, those points will have more influence than other values. So it works out that extreme values of x have more influence than other data points when it comes to regression. Well, if x is correlated with y, then it's reasonable to believe that the extreme values of y would go along with extreme values of x. And I don't see that here. So I'm not worried about an extreme value of x throwing off my model for these 3 points, well, 4, 3, 15, 23, and this mystery yellow point. And I like the fact that the plot doesn't appear to have like an order to it. Here's the square root of the absolute value of the residuals. And I usually rely on standardized residuals, not the square roots. Here's a Cox distance. You notice that I don't really see a pattern among the values. So if I saw them all on the far right or all on the far left, because I sorted the data, I would know that there would be something going on with the more extreme observations. but I don't see that here. Residuals versus leverage. Yeah, I'm not seeing anything going outside these contour lines. I don't really see, like a horizontal line is what I really want to see on these scribble lines, and that's close enough. Like these lines are going to find a pattern. So they're going to figure something out. So just because you see a scribble line doesn't mean there's a pattern there. If I see it being horizontal, there's no pattern. This is pretty close to horizontal. Here's Cook's distance versus leverage, and I don't see any major issues. All right, so now let's do the added variable plot to see, should we keep temperature considering that we have the other variables included? I conclude yes, that is a non-horizontal slope. Okay, so now let's look at density. And I say that that is a non-horizontal slope. So we would want to keep density. Now here, this is not much of a slope. So this is making me feel like rate should not be included in the model, which is consistent with everything we've looked at so far. So here, this is leading me to believe that temperature and density contains the informative value of rate. So including rate in the model would not add to the model overall. It can cause problems with my coefficients, which I suspect is going on. Looking at the initial summary output, it can make it overfit on my data, and it makes my model harder to interpret because it's more complicated. So I'm seeing that I should remove rate from this model. All right, well, that's all I've got for you. Take care and goodbye.